Okay, so today we will start with a new unit. So this unit is about neural network. And if you recall previously, we also learned the concept about perceptron. So basically, that's the simplest case of a neural network, a single neuron, okay? And we also learned the add-line. So that's some very, very basic idea, okay? So let's take a look about the add-line previously, what we learned. Basically, that's we call it a single layer, okay, neural network. And if you recall, so over here, so this X, so those are about the features, okay. And this is a bias term. So here we have features, feature values. And here is the weight. So the feature values are known values. And the weight, we don't know, it is unknown. And the purpose of the perceptron add-line is to train the network to find optimized weight. So that's the goal, is it? And if you recall, for the net input, so net input basically just the features times the respective weights, is it? And we add all of them together. So that's called net input Z, is it? And if we write as vector format, that's WX. So that's vector format. So anyway, so this is regarding net input Z, okay. And then we apply some, we call it activation function. Is it activation function? Then we generate some output, is it? And for add-line, the case is it uses linear. So basically it's just that sigma. The feature times the respective weights. Okay, so that's this activation function for add-line. Okay, for add-line. And then based on this output, then we use unit step function to predict the class. So this is a predicted result. Okay. So that's, so from the input features values and all the way to the predicted, etc. So this kind of calculation, we call it a feed forward. Feed forward, etc. And then based on the arrow, if you recall, for add-line, we learned the gradient descent. Because it involves multiple epochs to train, etc. Because initially you just assume some initialized weight values that's not going to be optimized, is it? Then we are going to apply the gradient descent. When we apply gradient descent, we use the real value versus the predicted value, etc. And regarding all of the samples, and you square it. So sum of the error, etc. Sum of the square of error, and then we take the gradient approach. And if you recall, take the gradient approach and then to find the update of weights. Is it? And then you update the weight. So we keep updating the weight. So each iteration, is it? Until we can find that this is going to be minimized. So that's the general idea, is it, about that single layer neural network. Okay, and here we have the concept of gradient descent. So the gradient descent, if you recall, it's based on, so here is a cost function. Cost function. So if you just have a single weight, then it should look like something like this, is it? So the best, so our goal is try to minimize the cost function. So this is the optimal point. So our goal is to find this specific optimal weight. Is it? How do we don't know. So you may start here, you may start somewhere, is it? And then we take the gradient descent, take a gradient. We take the gradient. So here is delta W and here is that delta cost. Is it? And with the gradient, with this relation, and we take, so the weight is updated that is weight, is it? So that's the gradient. So it's basically derivative regarding the weight, okay, regarding the weight. And so here is a learning rate. Learning rate, okay. Then we can keep getting the weight close to the optimal point, okay. So that's the whole idea. And basically, today we will see the neural network. So that's the very basic one that has a lot of same idea, is it? But we will see there's something different. Okay, so the artificial neural network, generally when we mention the neural network, we means multi-layer. Okay, so ANN, you may see this a lot. That's called artificial neural network. And it also called MLP. So MLP is multi-layer perceptron, not the single layer. Okay, not a single layer. Okay, so what is the idea about multi-layer? So multi-layer perceptron. Okay, so the idea is you are not just going to have a single neuron, you will have multiple neurons. Okay, and we are going to connect all of these single neurons together to form a multi-layer. And here is feed-forward neural network. Okay, and also it's fully connected. Okay, so here is an example. Okay, here's an example. And here we have, if you see, it's kind of, we have 3 layers. There's 3 layers. And this is the first layer, we call it input layer. So input layer directly associated with samples features. So basically A1, this A1 input layer is just this X1, okay, the input feature, a specific features value. Okay, and you have multiple features, M features, then everyone get to that neuron. Okay, and here we have this bias term. biased term. Okay, and then if you take a look over here, we have second layer. Second layer, we call it a hidden layer. Okay, so here with neural network, we also have a hidden layer. If you recall previously, when we discussed perceptron outline, we don't have a hidden layer. Okay, and here we also have a hidden layer. Okay, and regarding the values within the hidden layer, we don't know. Okay, it depends on the weights. So how it's connected is, this is the previous layer, input layers neuron, a single neuron. This neuron will connected with every neuron in the next layer. Okay, everyone. And the same thing for the next neuron, it's also fully connected. So if we take a look, is that it's also and the next, like suppose the next one is that it's also. So anyway, so the previous layers, one neuron from the previous layer, it's going to connect to all of the neurons to the next layer. So this we call it fully connected. Okay, so it's fully connected. And because it's connected here, basically it's just mean there is some weights associated with that link. Okay, so that we can do the calculation. Okay, do the calculation. So basically then, like for example, for this neuron, this A1, H value, then it's going to get all of the value from all of the previous layers neuron and plus the weight. Is it plus the weight? So what it will have is the previous layers values. So this is from previous layer and times all of the weight, is it? And the weight is regarding this layer's weight, but the weight we don't know for this weight. So we can see there are a lot of weights, is it? A lot of weight. Also depends on how many neurons you defined for the hidden layer, okay? And then we can also, so in this case, you can add more hidden layers, okay? But over here, we just add one hidden layer. Then over here, this is the output layer, okay? And for this output layer, so then that's based on how many target values you have, okay? So the number of the output neurons, so this depends on the target values. If you only have one target value, then you just have a single neuron. If you have more than one, then you have more than one target values. Okay, so it depends, okay? And then the same thing. So each neuron is also connected, is it, from all of the previous layers. So then you also have the weight. So the weight, we call it the output. Regarding output layers, is weight. Okay, so weight is going to that neuron. Okay, then the same thing over here, is it? So this A out, then it depends on what? Depends on hidden layers input and the output layers weight. Is it? This we don't know. And this one, if you take a look, it depends on the previous layer's calculation, is it? And then this part is also unknown. So we have quite a number of unknown weights then in this case for multi-layer perceptron. Okay, perceptron. And after that, then you can apply like either Adeline, not Adeline, yeah. So after that, then based on the values, then we can predict. So here is the output, the predicted values. Okay. So anyway, so overall, this diagram still explains the feed forward. Okay. Concept. Okay, we kind of get the idea about feed forward neural network. So then let's see how activation a neural network we call it forward propagation. Okay, forward propagation. This is a learning procedure. There are 3 steps. Okay, so at the input layer, what we do is we forward propagate the patterns of training data through network to generate output. That if you recall, you have input layer. Then over here, we have a hidden layer. That, and here we have output layer. That, and each is associated. That where like the weights. So here is a hidden layer, and here is the output layer's weight. So that's why we call it a forward propagate. And all these values are known values. Known values, is it? And then from here, you predict the y hat. So this is the target, is a predicted target values based on the output. Is it? So we generate output here. Okay. And this is based on the output. Then we need to calculate the error. And we want to minimize the cost. Is it? So the cost function can be different if you recall. Is it? We use sum of square of error. And we also have logistic regression. They use a different, so the cost function can be different. But anyway, so this is predict, and you also have the real one. So this is the real, is it? And then you need to know the difference between this, then the arrow. So then, so here is regarding the arrow, is it? Then you need to get the arrow back, is it? And update the weights. That's what we learned previously. But here with the MLP, multi-layer perceptron, here the arrow, we are not going to do this. Okay, not this one, let's use it. So here for the arrow part, we are not going to do the old way. So here we will see, we are going to do, we call it back propagate arrow. Okay, so the idea is you have arrow here, is it? Then you are going to do back propagate. Arrow. And then over here, then you will find the arrow, then you propagate back. Okay, so this is called back propagate arrow. And when we do the back propagate arrow, we are still going to use gradient descent concept. Okay, so here is we find the derivative with respect to the weight. Okay, and later on we will see, also explain why we needed to use backpropagate instead of the way previously that we learned. Okay, so we feed forward, okay, from the features to the predicted values. And then with the predicted value, we find the error, we backpropagate, okay, to update weights. Update weights. Okay, so that's the idea. Then it says after we repeat these steps for multiple epochs, so similar as previously, it involves multiple epochs, then we can find the optimal weights. Okay, with the optimal weights, then we use forward propagation to calculate the network output and apply some threshold function to obtain the predictor class label. Okay, and also we use one-hot representation. So previously we already learned this, is it? So the training part. So model training involves backpropagation. Okay, model training. And when you do the prediction, then we just use forward propagation. Okay, so that's the basic idea here. Okay, so then next, let's take a look more about the math background behind it. Okay. So first, let's take a look at feed forward. So forward propagation. That forward propagation, the very first step, if you recall. So over here we just assume 3 layers. So this is input layer. The input layer basic is just those X values, is it? And then here we have the hidden layer. Okay, so that's about this A hidden, is it? So this A hidden, and you have multiple unit, is it? Neuron. So for each of it, is it? Each of it, how do we find the calculation? If you recall, so this part, so this is those X value, so features, okay, feature. And this is the weight, hidden layers weight, each one of it, is it? So regarding single neuron, then it takes input from all of the other neurons, is of the other from the previous layer. So that's why here you sum them together, is it? From each sample. So this is regarding each sample. So each sample times the respective weights, is it? Then this is the net input, basic. In previously we call it net input, is it? But sometimes we also apply some activation function. Is it? So fine. Okay, so after you apply the activation functions, it can be like add-line, sigmoid, we have learned, is it? So those are called activation function. Okay, and that will generate the input for the hidden layer. Okay, so basically, then this you get the hidden layers result, that activation result. And then same thing. From this hidden layer, then we can have the result for output layer. That output layer, this A out. Okay, so it also depends on the input from hidden layer. That so by this we can kind of induce, is it? You first need to calculate the output layer's net input, is it? So this net input then is based on the hidden layer, is it, from hidden layer, and its weight to the output layer. And then same thing, then we can apply the activation function to this net input to the output layer. That once we get this output, then based on the threshold, then you can do the classification. Okay. And then let's see, the next one is that so similar. Okay, so here just the vector formatting. Okay. And then the vector formatting, and then from hidden layer to output layers net input, is it? It's the same thing. So this should be from hidden layer, and this is the weight to output layer. Okay. And once we have this, then same thing, we can apply the activation function. Is it activation function, suppose like sigmoid, is it, to find the output values. Okay. And with these output values, then we can do the calculation. Okay. So that's the theoretical background. Okay. Very broad discussion. Okay. Not to go too much detail regarding the math background. Okay. The general idea. So in sklearn, okay, regarding multi-layer perceptron, so the ANN, multi-layer ANN, etc. There are a couple of options. We can use stochastic gradient descent, or ADAM, or this LBFGS. Okay. So here to give brief description, okay, and you can read the official document for detailed description about each of this option. So stochastic gradient descent, so SGD, is as update parameters still using gradient of the loss function. So basically it's a cost function, is it? With respect to some parameter that it needs to adapt. Okay, so that's regarding stochastic. If you recall, stochastic, that means online, is it? And versus the batch. So batch means you need to go to all samples in memory. So in a lot of cases, that's even not applicable, etc. So online, you can do like one by one, or you can do mini batch, so that you don't need to load all samples into the memory. Okay. ADAM is that's similar. Okay, so it's also stochastic optimizer. But it says it can automatically adjust the amount to update parameter based on the adaptive estimates of lower order moments. Okay, so that's what this ADAM approach. The other one is the LBFGS. Okay, so this one it involves some other math background regarding Hessian matrix. Okay, so, and here it says with regarding LBFGS, then it does not support online or mini batch. So there regarding this, we can see it's only applicable to small set, small size data set. Okay, so be careful. For the other two, it can be applied to large data size. Okay, so that's some background information regarding these three different approaches. And then next, let's take a look. Now we understand the concept regarding forward propagation. Okay, forward propagation basically is just you keep do find z net input, is it? It's equals to that. So if we write as vector format, it's the input times the weight, is it, involving this, and then you apply the activation function to the net input, then you can generate the next layer. As it, so this is input, this is a hidden, is it? So similar, is it? Then you use the hidden layers input with output layers weight, then you can generate the output for hidden for output layer, is it? Then you apply the activation function to output, then you can find the output, is it? Find the output. With this output, then we can do the classification. So all this is feed forward, okay? So forward propagation. And if you recall previously, for the activation function, we can also using sigmoid as a logistic, okay, to serve as activation function. It's more efficient as sometimes compare with the add line, as it. So we already know the concept about the sigmoid and logistic. Sigmoid and logistic is not like the unit step, is it? Is it? So this is much more, so it's between 1 and -1, is it? So it's much more flexible, okay? The sequence, we also call it we squashed. Is it squashed? Okay. So that's a concept regarding sigmoid. And neural network in our previous discussion, we also discussed it. So this is just with one hidden layer, but we have 3 layers. We have input layer, we have a hidden layer, and we have output layer, 3-layer neural network, okay? And for the output, you just have a single neuron, etc. But just like previously we discussed, okay, be careful. So each neuron will take input from all the neurons from previous layer, okay? So that's why we call it feed forward. Oh, that's why we call it fully connected, okay? So we already understand all this, okay? And over here, we use G to represent our activation function, okay? So similar as that 5. But anyway, so here you have net input, then you apply some activation function, etc. And here there are more detailed discussion about the number of units, the dimension, okay? And so with logistic regression, if you recall, this is regarding single unit, is it? It's cost function, or sometimes we call it loss function. And if you recall, we derived, it can be expressed like this, is it? So this is also quite straightforward, okay? So over here, this A is based on the calculated result, is after apply the activation function, okay? And if you recall, this is L2. So this is used for the regularization to prevent overfitting, is it? And in sklearn, we use a parameter C, okay. So then that's for for multiple activation unit, then we can expand it, is it? And it can be expressed like this. You consider all samples, is it? And so the goal here is to minimize that cost function. Okay, cost function. But here we need to be careful, is it? And minimize cost function based on mass, we can take a derivative, is it? Regarding each weight. Is it each weight? But here be careful, when you discuss weight, we have multiple layers, is it? So here you have a hidden layer. So hidden layer has the weights, is it? And then for the output layer, is it? But for the output layer, if you recall over here, this A out, it also counts on the A hidden, is it? And A hidden, then it counts on the weights, this weights, is it? So when you take the derivative, this W, then it is also some function regarding the previous layer's weight. It's some kind of function, it's regarding it. So when you take the derivative, to out layer, then based on mass, then you need to take it's regarding that function. And then that function needed to take a derivative regarding that hidden layer. Is it? If you have more hidden layer, then you need to take this kind of derivative multiple times. Is it? So this kind of take a derivative and multiply together, this involves a large matrix. The calculation, so if we strictly follow the forward propagation, then this kind of calculation is too expensive. Okay, very expensive, not efficient, is it? So that's why there is a concept called back propagation. Okay. So for neural network, basically to use back propagation algorithm, okay, to compute the derivatives for the cost function, not directly, okay, and we will see it's a very neat concept, okay. Just like previously I explained, this is in high dimensional feature space, that weight coefficient can have some large number, that an arrow surface is not just what we previously saw, a convex or some smoothing. There may involve a lot of also local minima. Okay, you need to overcome to find the global minima, etc. So when you do the so this is kind of like some weight, is it? So the output layer's weight then counts on the previous layer. Then that previous counts on the previous hidden. So it may involve function over function, is it? So from math, we learned, then when you find the derivative regarding this specific parameter, that involves a partial derivative, is it? All the way to the last one, is it? That's why I said the forward is very expensive, okay, due to multiply large matrix for each layer. Okay, so that's very expensive. So reverse is cheap, okay, because reverse, then the mathematician derived, then basically it's not you multiply multiple huge matrix. Instead of that, you multiply a matrix by a vector. Okay, so that's much cheaper. Okay, so all this expression previously we already explained, is it? So this is over here it's from hidden layer, is it, to output layer? Okay, to output layer. Okay, so here then there is a concept is that in back propagation is we propagate arrow. So from back, from output basically to input. So from right to left in this diagram. Okay, so the arrow vector here is that this is regarding output layer. Okay, so this is calculated, is it? Calculated output. This is the real one. So the difference then is the arrow. So for the output layer, this arrow calculation, no problem. It's pretty straightforward. But the problem is for the hidden layer. Okay, then regarding hidden layer, let's think about, so here you have, so this is output, this is input, then hidden, this is output, is it? So for output, it's straightforward to find that arrow, is it? So it's just A out minus Y. So that's straightforward, we can find. But for each of it, here we also have arrow term. Why we see here is arrow term? Because if it's a perfect one, then your weight should be a perfect weight. The perfect weight, so suppose we call it a perfect. Is it the perfect weight times the previous layer's input? Then it should generate a perfect one. So this should also be a perfect one. Is it? But as we discussed, this calculation is started from trial weights. And because it's trial weights, is it? So there is, so this is the trial one, is it? And you times the input, you will get, this basically is the trial one. So trial one and the perfect one, definitely there is error, is it? That's how we call, here is the arrow term for the middle layer, is it? But some mathematician already derived this hidden layers arrow. It basically depends also on output layers arrow and the weight to it, as well as the derivative of the cost function to that specific net input. So this is regarding the derivative to the net input of the cost function. Okay, so over here, so this is a scalar, this is a vector, and this is a matrix. That's why we see over here, then it only involves you calculate a vector and a matrix multiplication, versus previously you needed to multiply multiple matrix, is it? So that's why we see over here, this is much better, okay? And in the case of sigmoid, then the derivative is also quite easy. It's just hidden layers input, is it? And also for this calculation, this is element-wise multiplication. So this is also not too expensive regarding the calculation, is it? So then for sigmoid case, then the hidden layers arrow, then it's based on output layers arrow and the weight, and this value we can also find, is it? So that's why hidden layers arrow depends on output layers, is it? That's why here we call it back propagation. Is it? So you back, and then from, suppose this is a hidden layer, is it? Then suppose you have another hidden layer, then to keep push it back, is it, from the output and the hidden and all the way to the input, okay? So that's what we call back propagation, is it? So basically, then we say the derivative, previously we take the derivative, is it, regarding the weight, and we don't need to directly do the math way, is it? Then we can find out the relationship is the output, the arrow, is it, times the input. Then for hidden layer, it's the same thing. Okay, so we can find this relationship. And because of this relationship, then we don't need to do this derivative directly. Okay, so no need do derivative directly, is it, on W anymore, is it? So that's changed the way. Okay, and if you recall, is it, for gradient descent, so this delta, this part is this gradient, is it? This is the learning rate. Learning rate, okay, and previously, if you recall, in all of our previous discussion for gradient descent approach, we need to find this way, is it? And now for this calculation, we don't need to directly do it. We can use from the next layers result, is it, to find the result, okay, to find the result. So anyway, so for the output layer, when you want to take it, the derivative for the gradient, then this is just the output layer arrow, and this is its input. This we can find from the feed forward, is it? And once you find this one, as I find this one, then the arrow from the hidden layer, we already find the relationship between the hidden layer and the output layers, is arrow relationship, is it? And this value we also know based on the previous calculation, is it? So once you know the hidden layers is arrow, is it? Then you can find its derivative, is it, to each respective weights, is it? So then you can borrow this relationship, find the derivative. And once you know the derivative, then you can update the hidden layers hidden layers is gradient, is a gradient. So then we can update the weight. So that's why we call this back propagation. Okay, so that's regarding multi-layers neural network, how the feed-forward workings and how the back propagation works. Okay, I think today